with the idea that if you have a base raised to a power on the left side of an equation, and that same base be raised to the y power on the other side, what could you assume then? X must equal y. Exactly. Then x has to equal y. So if you get a common base, the same base on both sides, then you can just set your exponents equal to each other. Okay? So in the first example, and we're going to have to do some exponent rules here, you're going to see, you can rewrite 8 as what to what power? How can you rewrite 8? 2 to the third. So there's my rewriting of 8, and it was being raised to the x power. And so that's where your exponent rules are going to come up, because power to power means multiply. So that's the same as 2 to the 3x equals. On the right side, how can you rewrite 32? 2 to the... I'll help you. 5th. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Yeah, 5. So now that your bases are the same, I can just set my exponents equal to each other and solve. Divide both sides by 3. Good? And you could check that. 8 raised to the 5/3 power. That's what x is. It's supposedly 32. Perfect. Okay? B. How would you rewrite 9, Aiden? 3 squared. Keep that in parentheses because it's still being raised to the 2x plus 1. 27 is 3 cubed. Power to power means we multiply. What do we have to remember with multiplying here? Distribute, because you're multiplying 2 by a binomial. So that's going to be 4x plus 2 equals 3 to the third. Bases on both sides, drop them. So 4x plus 2 equals 3. Subtract 2 from both sides, so 4x equals 1. Divide by 4 on both sides, x equals 1/4. Good? Now, just out of curiosity, if I plug in 1/4, what's 2 times a fourth? A half. A half plus 1 is 1 1/2, which is the same thing as 3 halves, right? Just a weird connection to make. Remember our exponent fraction rules. This is the same as the square root of 9 cubed, right? Square root of 9 is 3. 3 cubed is 27. Just all this stuff is kind of intertwined, is why I'm just kind of bringing that exponent radical rule. And then in C, 125 is 5 cubed to the x power. What about this guy, 1/25? 25 is the same as 5 squared, so it's 1/5 squared. But we can't have one base in a denominator and the other in a numerator. So how do I bring this one up to the numerator? What is that going to do to my exponent? Negate it. So this is the same as 5 to the negative second to the 4 minus x. So power to power multiply here is going to give me 3x. Power to power multiply over here, distribute, is going to give me negative 8 plus 2x. And then I would solve. So subtract 2x from both sides. X equals negative 8. Okey-doke. Okay, so do you see how they're all coincidentally like working out for you? Okay, just for today. And then we'll talk about what to do when they don't. Like last night's homework was this equation, that 10 equals 84 times 0.76 to the x power. The base is 0.76. I don't really know how to rewrite this as a 0.76, so we wouldn't be able to solve that still. Exercise 4, this equation, base of 2 on the left is all good. Base of 64 needs to be rewritten as 2 to the 6th, right? If 2 to the 5th was 32, that's 2 to the 6th. So this one is just unique because what kind of equation results when you drop your bases? What kind of an equation is this? Not linear anymore like the other 3 were. Quadratic. So you'd add 3 to both sides. Again, because I don't have a b term, I don't have a plain old x term, I don't have to factor. I don't have to do the quadratic formula. I can just solve by square root. So x equals what? Plus or minus 3. Good. That's option 1. Okay, yep. Yeah, because you're only giving one of the solutions, right? If the solutions were, even if they weren't opposites, let's pretend you did a quadratic equation and the solutions were 2 and 5. If you just put 2, would you lose points? Absolutely. You missed the second solution. And the same would be true if you forgot your plus or minus. You would miss your second solution. It's a good question, though, because it seems, I mean, would you probably lose as much credit? No, because you just forgot, like, the plus or minus. Whereas in the other one, you kind of must have missed a whole bigger concept. No. Exercise 6 here is really asking the same thing, but it's in the way of asking, like, you to solve a system. When will this graph cross this graph? So since they both equal y, you can set them equal to each other. So 25, is that an a? Yeah. To the x minus a needs to equal 1 over 125 to the 3x plus 1. So 25, that's easy, right? 5 squared. What about 1 over 125? Andrew? 5 to the negative third. Awesome. So power to power on the left is going to give me 2x minus 2a as my exponent. I'm going to drop my 5s now. Power to power on the right is going to give me negative 9x minus 3. And this is asking me to solve for x. So I got to get all of my x's together. So I got 11x on the left. I'm also going to get rid of the non-x's, so I'm going to add 2a over. This is a little bit odd because we have to do the solving for x in terms of another variable. So we're not going to get a number answer. And then when I get x all by itself and divide by 11, I get x equals negative 3 plus 2a over 11. So which one is my answer? 2. All right, what do we got going on here? Two exponential curves again. This one is labeled here, and this one is labeled here. They intersect at point A. Can we find point A or no? Let's just do that. I'm not even going to read the question. I'm just going to assume we should be able to find point A. Where do these two graphs intersect? They both equal y. Set them equal to each other. So I'm going to set 4, and I'm going to use my space down below. 4 to the x plus 5 halves equals 1/2 to the 2x plus 1. And Grace, 2 squared, good. And Evan, what do I do with 1/2? No. Let's go back, Evan, to the front side. Your friend Andrew, who's been paying very close attention, took 1/125 as a fraction and changed it to 5 to the negative third power. He knew that because in 3C, I took 1/25 and explained, and we chatted about why that's 5 to the negative second power. Do you see? So the fraction creates a negative exponent. That's the first thing. So to get that 25, or the 5 squared, out of the denominator, we have to move it into the numerator but make the negative exponent. And so 125, which was 5 cubed, I got out of the denominator by making it 5 to the negative third. Okay, so being that this is in the denominator, it's currently 1/2 to the first. So if I want to get it out of the denominator, what do I rewrite it as? 2 to the negative 1. Good, thank you. Nice job. 2x plus 1. Now in my power to powers multiply, so this is 2x plus 10 halves, which is just 5. And this is distributed negative 2x minus 1. Add 2x to both sides. At the same time, I'm going to subtract the 5 over to the right, and I get 4x equals negative 6, so x equals negative 3 halves. So the x coordinate at where these are intersecting is at negative 3 halves. So that coordinate right there, negative 3 halves. What dimension then do we know about this rectangle? The left side's length, the bottom's length, the right side's length, the top length, what is it? If we know this x coordinate is negative 3 halves. Andrew, the top, how long is that? Well, length is always positive, right? So 3 halves. And in order to find out the width, I need the y coordinate, right? This other side length, I need the y coordinate, which is easy because once I know the x coordinate, I can just plug it in to find the y. Y equals 4 to the negative 3 halves plus 5 halves. What's negative 3 halves plus 5 halves? How many halves? 4 to the 2 halves, which is 4 to the first, which is 4. So if the y coordinate is 4, this length is 4. And so when you know the length and width of a rectangle, you can find its perimeter, you can find its area, whatever. So part A was kind of going to get us thinking along this line. Fundamentally, what do we need to know about a rectangle to find its area, length, and width? How would knowing the coordinates of point A help find the area? Because the x coordinate gets us this length, the y coordinate gets us that length. So find the area. It's just 4 times 3 halves, which is 12 halves, which is 6. Units squared. Do you remember that from little kid school? Units squared. Do you remember that, Nate? Remember doing units squared when they didn't tell you? Oh, little kids math was so much better, wasn't it? All right, question for you. I'm going to give you this exponential equation. Yeah. Yes, you may. What is the y-intercept? Bo says 3. Nate says 7. Yeah? Mason, be careful. I would die if you fell and slipped and went and nailed your head. Don't do that, please. Don't do that, please. I would not be thrilled. I'd be freaking out, probably. There'd be blood. I wouldn't like it. Wait, why did you say yes, Mason? Why are you sold? He's like sold hook, line, and sinker. What? 12! We got a new option thrown on the table. Mason? You said, like, yes. Like, you were convinced it was 7. Why? I like his initial step. I don't like where that explanation kind of spiraled out of control. Maggie? So like here? Correct. So it is 7. The AB to the X graph. A is your y-intercept, so that's why Bo said 3, right? He's like, oh, it's the A. It's only the A if it's just AB to the X and no more. But Maggie hit the nail on the head. It is 3 right now, but then you're shifting everything up 4, and 3 shifted up 4 is 7. But I like where, that's one explanation. Mason's was just y-intercept. Plug in X as 0. So if you plug a 0 in, 2 to the 0 is 1. Then it's 1 times 3, Mason. This is where we kind of went off the beaten path. It's 1 times 3 is 3, and then 3 plus 4 gets you 7. So either one of those explanations would be good. What about this? Nate? I don't think so. How did you get 19? Right. 2 to the 4th power is 6. Oh, no. Why did you add 3 to 16? You should have multiplied. This has a y-intercept of 48, okay? That's pretty much the only way you're going to do this one. The parent graph is this, right? So 0, 1, and 1, 2, right? 1 comma B. 0, 1, and 1 B. 1, 2. What transformation occurs first? From here, moving towards this. Order of operations. What happens first? Exponent. We're going to move this graph how? Left 4. You're adding 4 within the graph. Within his horizontal. So left 4. So 0, 1 moves over to negative 4, 1. So let me just take my critical points and show how they move with each transformation. 0, 1 shifts left 4, so it's going to be negative 4, 1. And 1, 2 shifts left 4, so it's going to be negative 3, 2. Then what happens? So now our graph is like this. So already our y-intercept is way high, right? And then on top of that, it's getting shifted, or transformed, I should say. How, Nate? Stretched by 3. So already it was high. If it's just this, what's the y-intercept? If we just had the left shift by 4. 16. So already the y-intercept was at 16. Now on top of it, we're now stretching everything. So this point, vertically stretched by 3, means vertical times that by 3. Negative 4, 3. Stretch that by 3 would be negative 3, 6. And then that y-intercept that in the interim was at 16 has now also been stretched by 3 to 48. Okay? This is something that just dawned on me today. What do we think of this? Yep. 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 Flips it over the x-axis. So here's your parent graph. What's the y-intercept? Better question. Negative 1. Yep. Because your parent graph 3 to the x is here was 0, 1, and 1, 3. And then we flip it over the x-axis, which negates our y-coordinates. So now we have 0, negative 1, and 1, negative 3. Good? Here's the thought that this is the third year in a row I've been teaching this, that it's never been asked before, but it just got me thinking. Would you say that this equation is exponential growth or decay? I honestly don't even know if they could ask that question, because it is growth based on the fact that this is just being raised to the x power and your base is 3. So its base is greater than 1, it's growing, but it's growing in the negative direction, right? So it's actually decreasing super fast. So it's growth because you keep multiplying by a number greater than 1, so it's growing, 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 but it's growing into a larger negative number, which we all know makes it smaller at the end of the day. So the answer to that question is I don't know. But I had that thought this morning, and I wondered, so now I'm going to take it to Mr. and Mrs. Hill and see what they think. But I don't think they could honestly ever ask that, because I think it's too tricky. I don't know if there is an answer. It might be one of those that is explain why you chose what you chose. And if you said growth because the base is greater than 1, I think that's the good explanation. If you said decay because the graph is decreasing, I think that's also a good explanation. Anywho, that's all I got for you. This is a rare occasion, isn't it? And I had to add extra stuff in as it was. Would you look at that? All right, so homework is coming.